Had we been in class, I would have posed this little equation to you and asked you to solve for x, something we like to do in math. But look where x is now. Right, it's in the exponent. Now maybe you have a technique that you would use to solve for x, or maybe you would just use some guessing and checking. If we use some guessing and checking, we should know that x can't equal just 2, not big enough. And of course, if x equals 3, too big. So maybe x equals something between 2 and 3, like maybe 2.5. Well, it gets us a little closer, but we know that's still too big, so maybe we could try something lower, like 4 to the 2.2. Still a little bit too big, but getting closer. Now, if you use 4 to the 2.1, you've gone too far. So now we have a little bit of a baseline. We know it's got to be 4 to the 2.1, maybe 5. Maybe 4 to the 2.16. We're getting closer. Now, if we use 4 to the 2.17, we know we've gone over, but are you starting to get a feel here that there definitely is an x, there definitely is an exponent. It's going to be a decimal. It's going to be 2.1. Well, to 3 decimal places, maybe 2.161. Of course, that's still a little bit too big, but we can see that we're getting really close to our value of 20. Now, this exponent that we're trying to find, well, you see, it's actually equal to a log. In fact, it is equal to the log base 4 of 20. But maybe you say, what is that? What's the log base 4 of 20? Well, from a beginner's look, it's an exponent, and it's a number. But how do we get it, and what does it mean? Well, let's back up a couple steps, and I want to go through a little bit of the theory of logarithms, something that I find most students are thankful to see. And slowly but surely we will build towards what are logarithms and why do we need them. I think everyone in the crowd would say that 3 squared equals 9. That is a simple math statement that we would say is in exponential form. But there's a logarithmic form that actually makes the same claim. It just says it in a little different language. You see, it would say that the log base 3 of 9 is equal to 2. Now, here's the thing. Both these statements are making the same claim. And the claim is that when you have an exponent of 2 on a base of 3, that's going to equal 9. Getting a little bit of a reminder about logarithms. Let's do another one. How about 4 to the 1/2? Now remember, 4 to the 1/2 is the same as the root of 4, so we should be able to say that is equal to 2. But we can make that same claim using logarithms. We could say that the log base 4 of 2 is equal to 1/2. And so that is making the same claim. And are you starting to see something that's true for all these log statements? That is that they are always equal to the exponent. How about e to the negative 2? A little fancy. I don't expect you to write that as a decimal, but we could write it as 1 over e squared. Well, can logarithms handle something of this form? Something where we have a base e? Well, sure, the log base e of 1 over e squared, now that would have to equal negative 2. And again, we see that this logarithm is equal to an exponent. But we also see that we have a log that has a special base. We have a log base e. Log base e's have their own logarithms. They're called natural logs. And so we could say that the natural log of 1 over e squared is equal to negative 2, which would be making the same claim, just a little bit more mathematically correct with the notation. So what do you see in all these cases? Well, I want you to see that whenever you have a basic exponent statement like b to the x equals a, you can make that same statement using a logarithm, where we would say that the log base b of a would equal x. And again, notice that the log is always equal to the exponent. If we had e to the x equals a, just a special base e, well, that would be a special base logarithm. We call it the natural log. And so we could say that the natural log of a is equal to x. And once again, we see that a logarithm is always equal to an exponent. In fact, that little phrase is something worth repeating. I find that it helps students understand logarithms because logarithms are exponents. So what we can do now is get into some simple evaluating. And this is kind of fun because we're just thinking about numbers. And so if you wanted to figure out the value of the log base 6 of 36, you'd be thinking exponents. That's right, you'd be thinking what would be the exponent that you could put on 6 to get 36. And of course that exponent would be 2. So the log base 6 of 36 equals 2. Do you want to see if you can figure out the log base 3 of 81? What would be the exponent that you would put on 3 to get 81? And that exponent would be 4. So logs are equal to exponents. How about the ln of the square root of e? Now, before you get your calculator out, you want to be thinking exponents. And so maybe it'd be helpful if we change a square root to an exponent. Now, the base e is always assumed with an ln. You can write it down if you want, but the real key to this problem is that you should be thinking about that red base e to what power is going to equal e to the 1/2 power. And you don't necessarily have to write that out, but that's what you want to be thinking so that you can say that, well, the exponent would have to be 1/2. How about the ln of the 6th root of e squared? Now remember, you want to be thinking exponents, so we could convert this to a 2 over 6, which of course is a 1 over 3. And once again, we're able to deduce that magic exponent would have to be 1/3. How about the log base 4 of 32? 4 to what power equals 32? Uh-oh, did we hit a little snag? Well, maybe we can think of both of the sides of this equation as the same base. And it turns out if you know your bases, you would be able to think of both sides as base 2's. Conveniently, then I can match my exponents. And so it looks like if I can write these both as base 2's, then of course my exponents would have to be equal. And we end up with 5/2. Now, that worked because we could make the bases the same. Do you want to see if you can use that same base matching technique on the log base 3 of 1 over 9? Go ahead, give it a try. So 3 to what power equals 1 over 9? That would be like asking 3 to what power equals 3 to the negative 2. And we have our answer because the exponents have to be the same. This logarithm is going to equal that exponent. So the log base 3 of 1 over 9 equals negative 2. How about this joyous problem where we have 2 logs? Now the ln of e to the 5th minus 3 the ln of 4 is actually asking for 2 exponents. And so e to what power is going to equal e to the 5th power? Well, that would become the 5, or that 5 power. And over here, we're just able to ask ourselves e to what power is going to equal e to the 4th power. And we could say that that would be that 4th power. And so I'm kind of doing the order of operations here. I'm figuring out the value of the logs so that I can then, of course, subtract those subsequent values. So we could say that the final answer here is negative 7. Now stick around because before the end of the lesson, we will also talk about how to use properties to deal with a problem that has addition and subtraction. How about the log base b of 1? It's like asking b to what power is going to equal 1. Oh, that's always going to be the 0 power. That's always going to equal 0. We call that a little property of logs, where the log base b of 1 is always equal to 0. And how about the log of 100? Yes, the log of 100. What happened to the base? Is it just any base? Well, no, it's not. You see, when the base is not written, we call this the common log. And the common log is assumed to have a base 10. So what this problem is really asking is 10 to what power equals 100? Well, of course, that would be 2. So remember, if the base is not written, we call that the common log. And it is assumed to always be a base 10. And how about the log base 7 of 40? The log base 7 of 40. 7 to what power equals 40? Well, it looks like we have run into a snag, at least a no calculator snag. So there has to be a way that we can evaluate this on our calculator. And instead of using a guess and check method, what we're going to do is use logarithms, specifically what's known as the change of base formula. Now for this problem, the change of base formula would say that I could actually do the common log of 40 divided by the common log of 7. And when you compute both of those common logs, which we'll show you in a minute on the calculator, we would be able to have evaluated this overall log. So the change of base formula says that if I have basically any base, any log base b of a, I can always do the common log of a divided by the common log of b. And students will often ask, this works all the time? Yes, it works all the time, as long as you always divide by the log of the base. You want to set it up the right way so you're dividing by the log of the base. So if we return to our little problem here, we can just type in the log of 40, use the log button on your calculator, divided by the log of 7, and we find this exponent. We basically find the value of this logarithm. Usually we'll write this out to 3 decimal places to be 1.896. Now a couple things. When you use the log button on your calculator, it is in base 10. It is already the common base. So you don't have to type it in. You don't have to worry or wonder if it's there. Again, the log button on your calculator is the common log button. It is in base 10. So how about our little equation from the beginning of the period? Wasn't x really a logarithm? Didn't x really just equal the log base 4 of 20? And now we have the ability to compute this by using the change of base formula, by taking the log of 20 divided by the log of 4. And when you do that simple division, you end up with our magic number, that 2.161 as the exponent. What if I had asked you to find the exponent to put on the e to get 40? Well, again, since logs are exponents, you would be able to interpret this statement as a log base e, but a log base e is an ln, so it'd be the ln of 40, and that would equal your x. Now you do have an ln button on your calculator, so you don't have to use the change of base formula. You can just use that ln button to end up with 3689. Do you understand what 3689 really is? It's really the exponent. And so if I plug in 3689 back in for x, so e to that 3689, well, I would end up getting 40. Now, I hope you understand that logarithms are exponents, and they can also help you to find exponents. So next what we're going to do is look at the properties of logarithms. And the properties of logarithms allow us to expand and condense logarithms. That is, work with statements that use more than one logarithm and understand how to correctly combine them together. Now, the properties of logarithms are much like the properties of exponents, because logarithms are exponents. So we first have what's known as the product property. Now the product property says that if I have the log base b of m times n. Now, the parentheses are not normally written, but they would be assumed to be like this, so I'm doing the log base b of mn. Well, that would be the same thing as having the log base b of m plus the log base b of n. We turn this into an addition problem. And look what we're adding. We're adding two logs. But since logs are exponents, it's kind of like we're adding exponents. Wait a minute. When do we add exponents? That's right, in a multiplication problem. When multiplying, you add the exponents. And so we're just trying to show you that this product property really comes from a property of exponents. Next, we have what's known as the quotient property. Now, the quotient property deals with a statement of division, and it would be like saying if I had the log base b of m divided by n. Well, that would be the same thing as splitting this up into be two logs that are subtracted, namely the log base b of m minus the log base b of n. Do you see what's happening here? We're subtracting logs. That'd be the same as subtracting exponents. When do you subtract exponents? That's right, when you have a division problem. So when dividing, you subtract the logs. And notice that you always subtract with the denominator. You always subtract the denominator for the quotient property. And lastly, we have what's known as the power property. Now, the power property is my favorite because what it does is it takes an exponent, like in this case, the log base b of m to the p. So here we have p as an exponent, and it takes that exponent and it makes it come tumbling down. It makes it come out front. So if I have a statement of the log base b of m to the p power, I could write that as p times the log base b of m. And again, notice that what's happening is the exponent is coming out front. Now, this also comes from exponent properties from the beginning of the chapter, because what we really have here are two exponents. A log is an exponent, p is an exponent, and what happens when you have a power to a power? Well, that's right, you multiply them. So we turn this into a multiplication problem. All right, so what can we do with these properties? Well, one thing we can do is we can expand logs. What that really means is we can take a single log and we can expand it into multiple logs. Now, in order to do that, what you want to see in this problem is that we actually have three different operations. We have a 4 that's being multiplied by an x squared. Now, we could stop right there because anytime you have something that's being multiplied, you're always able to split that into an addition problem. So I can write this as the log of 4 plus the log of x squared. Now, when you really get on the ball, you're going to say, but this x squared, this square is actually an extra power that really comes tumbling down and goes out front. So we'll take that 2, and I'm going to replace it. I'm going to stick it out front just to, again, get ourselves to this final answer. So we turn this into an addition problem, and then we notice that there is also division, and division becomes a subtraction problem. And so I could also write this, or I could finish this by writing it as minus the log of 9. So take a look what we did. We expanded this single log into 3 logs that are being added, subtracted, and we even brought the exponent out front. You say, well, why would I want to do this? Well, because maybe you have a problem like this, the log of 6, and you want to try to split that into actually simpler logs. How? How could I split this into simpler logs? Well, you have to see inside of the number 6. And inside of the number 6 would be two numbers that multiply to be 6. And what can you do with two numbers that multiply to be 6? Like maybe 3 and 2? You can split them into 2 logs. You can split them into the sum of 2 logs, like here the natural log of 3 plus the natural log of 2. But you say, Mr. Naylor, I'm in more of a division mood. I see inside of the number 6 a 12 divided by 2. Well, you certainly could see that because that could be split to be the log of 12 minus the log of 2. Now, the log of 12, now that we're talking about it, that actually has numbers inside of it. And what numbers are inside of 12? Well, when you get good at this, you'll break it down to its prime factors, and you'll say that there's a 2, 2, and a 3. And so what does that mean? That means I can write this as the sum of, let me use the right colors. Since we're doing a sum, we're going to use gold. So it'd be the log of 2 plus the log of 2 plus the log of 3. And, I still have this minus log of 2 hanging out. And so what do you see? I hope that you see that these logs will cancel. And interesting, we end up still with the same answer. Properties of logs. They allow us to work with logs. They allow us to expand them. And they also allow us to condense. Now, condensing would be the opposite direction, where we try to take what was 2 and turn it into 1. Now, I'd like you to see that whenever you have a coefficient on a log, that always is destined to come up as an exponent. And I'd also like you to see that since we have a subtraction sign, we're going to create a fraction. I like to help students understand that the final answer is going to be 1 log. So write down 1 log. Create a template for a fraction. And now we can start to put everything in its place, such as the x to the 5th in the numerator and the 9 in the denominator. Now students will say, well, wait, how'd you know where to put what? Well, here's the answer. Whatever's being subtracted is always going to end up in the denominator. And whatever's positive, see, technically this x to the 5th, technically this front log right here was a positive 5. So whatever's positive is always going to end up in the numerator. Now, a common mistake is for kids to see this subtraction sign and say, hey, I know subtraction is going to be a fraction, and then go to the business of writing out a division of 2 logs. I want you to see that this would not be the same as our correct answer. This actually uses 2 logs to divide, and that looks a little bit more like the change of base formula. But the bottom line here is that this division of 2 logs is not equal to the log of the division of just x to the 5th over 9. Okay, so be careful that we don't use the change of base formula as a substitution for properties of logs. This looks like a neat problem. Do you want to see if you can condense this on your own? We've got 2 to the ln of 3 plus 3 to the ln of 4 minus 2 to the ln of 6 minus 4 to the ln of 2. I'm telling you, if you can condense this all to be 1 ln of maybe 1 fraction, you'll be going down the right path. Now, if you notice that we always will bring coefficients up as exponents, you actually have to do this first, because once you bring the coefficient up as an exponent, then you will have individual logs that are added and subtracted. And once you have individual logs that are added and subtracted, you're able to say that whatever is being added, or maybe we would say whatever is positive, is going to end up in the numerator. Now, 3 squared is the same as 9, 4 cubed is the same as 64, and whatever's being subtracted, whatever's negative, is going to end up in the denominator. 6 squared is 36, 2 to the 4th is 16. Now, the only way to attach 36 and 16 is with another multiplication sign. But don't worry, since both of those are in the denominator, it is true that both of them are still being divided. Now, with a little bit of reducing and canceling, maybe the 9 and the 36 can reduce and cancel to be 1 over 4, and the 64 and the 16 can reduce to be 4 over 1, we find ourselves staring smack dab at the ln of 1. The ln of 1, that'd be like asking e to what power is equal to 1? Well, remember, the ln of the number 1 is always going to equal 0. Now, all these properties of logs, they're nice and all, but what are we really going to use them for? Well, how about a proof? Right, that'd be a perfect application of a property. We could prove or verify that maybe 2 logs are equal. Now what this really is just an exercise in some critical thinking, how to start on maybe the left side and try to make it equal the right side. I like this problem because there's actually two really nice ways that you could work from the left side. One of the ways is that you actually could just think of this 1 over 100 as 100 to the negative 1 power, a nice use of negative exponents, which then allows you to take this coefficient out front and bring it back up to interact with that exponent. Now, of course, they're going to interact by multiplying, because what we're really doing is we're bringing another negative 1 up here, and so that's going to cancel just to be, well, a positive exponent, a 1, and all of a sudden we have our answer. Maybe that's not what you were thinking. Maybe you were thinking, Miss Naylor, there's a fraction here. I thought you said fraction means subtraction. Well, certainly I could actually split this into 2 logs, being careful to make sure I subtract the log of 100. And now I was keeping our negative sign out front so that it could actually distribute or apply to both of these. That's a little bit of the trick to this problem. So now I have negative the log of 1, but I have positive log of 100. Well, the log of 1, remember, the log of 1 is always equal to 0. And so thank goodness, because now we're able to see that we get the log of 100, which of course is equal to the other side of the equation. Do you want to try one of these on your own? You don't? Well, I do encourage you to pause the video and just do some of the hard work of starting to develop that critical thinking skill where you can somehow take, in this case, probably the left side and try to make it look like the right side using properties of logs. Now, I think a great first step would be to take the fraction and make it subtraction. Next, we want to be able to recognize that the log of 1, that's always 0. That's a really nifty fact to remember. So now we're really just left with negative log base 3 of 162. Next, you're going to want to start to notice where I'm trying to go. And specifically, I'm trying to go to the log base 3 of 2, focusing mainly on this number 2. You see, what I could do is I could split up my log to be 2 numbers that multiply to be 162, but I'm purposely going to let one of the numbers be 2. And so 81 times 2 is a perfect split, because that's going to give me half of my answer already. That's going to give me the log base 3 of 2. And it turns out that my log base 3 of 81 ends up conveniently taking care of my other number. Of course, that becomes the number 4. So when you distribute this negative sign into the parenthesis, you end up getting exactly what we need. That is negative 4 minus the log base 3 of 2. All right, well, I think that's enough fun for one day. Wait, you say you want a little more fun? All right, well, here, take a look at this one last joke. People have 10 fingers and 10 toes. It makes sense to use base 10. Naturally.